Hello everyone, I'm Hemregmi, a graduate student from University of South Carolina. My research interest includes the ubiquitous sensing, millimeter wave network design, and implementation with machine learning algorithms. Today I would like to present one of our research work, Argus, predictable millimeter wave picocells with vision and learning augmentation. This work is completed by myself with guidance from my advisor, Dr. Sanjeev. So big question here is why we need 5G networks as contrast to existing LTE networks. 5G enables VR, AR applications that helps to revolutionize the health, industrial, autonomous driving, and multiple sectors. It also enables accurate indoor localization under low light conditions. These are only few examples, while 5G helps to improve in multiple sectors. With these 5G enabled applications, 5G users are growing each year significantly. For example, the graph shows the number of 5G subscriptions in North America is already around 54 million in 2021, despite COVID setbacks, which is expected to reach 280 million by 2025 in North America alone, which is almost 4 times increase in just 4 years. To achieve this goal, we need to deploy thousands and thousands of additional small range access points called Picocells, and majority of them will be installed inside indoor settings, where we also need to consider non-line of sight path for better network reliability. However, question is how we can deploy them effectively. Can we deploy them without any prior knowledge of the environment? Or we need to understand the environment properly where we are deploying them. Let's first look at what happens when we deploy them at corners, which is also called common sense deployment. For example, we have 4 picocells and we place them at 4 corners as shown in the figure. In figure, the x and y axis represent the 2D location of the client and the picocells, and the color represents the signal strength received at that location. We clearly see that the most of the locations have very low signal strength. Now, if we deploy these picocells, considering what kind of surrounding objects environment has, then the deployment location will be different. And also, we can clearly see that we have now large number of locations with higher signal strength. Hence, it suggests that we need to deploy the picocells cautiously in the environment to utilize available non-line of sight paths. Before we jump into understanding of the environment, let's understand the difference between the line of sight path and non-line of sight path. Since 5G operates at a high frequency, millimeter wave devices use the combination of antenna to focus towards one direction and creates highly directional beam, which is called beamforming. So picocell sends millimeter wave signal only at certain direction. If it can find the client in line of sight, which means there is no blockage, then the picocell can establish a link to the client. But what happens when something blocks the path between the client and picocell? Then picocell must find a way to send the millimeter wave signal to the client. Since 5G is operating at high frequency, different objects such as wall, table, chair, TV screen acts as a strong reflector and can reflect the millimeter wave signal back. So now picocell can steer its beam towards such a strong reflector and send the millimeter signal through such non-line of sight path. But in order to happen this, we should install the picocell on correct location so that it can establish such path. But now think about the scenario where we deploy the picocell at wrong location. Then picocell tries to steer the beam towards the reflecting object, but it never reaches towards the client because actual path is different than the path required to establish a link. Clearly, this indicates that we need to know the environment better before we can deploy the picocell so that it can establish a link via non-line of sight path. To understand more clearly how picocell location matters, let's add more strong reflector and client in our analysis. Also, let's assume we have line of sight path between the picocell and the client is blocked, and the picocell can only send millimeter wave signal via non-line of sight path. We can see that only client 2 is able to establish a link to the picocell through strong reflector 1, while other clients does not have any link. Clearly, one way to support more client is to add more picocell in the environment. Now we can see that adding picocell 2 is able to support client 4 by steering beam towards strong reflector 3. Still, client 1 and 3 does not have any link. However, if we change the location of picocell 2, then we can support client 1 as well as client 4. Client 1 can be supported by steering beam towards the reflector 1, and client 4 can be supported by steering beam towards reflector 2. This again explains in detail how location of picocell matters in the given environment to support maximum clients. So how we find the best picocell locations? One way is to do the brute force search by placing all available picocells in every possible location. We can see that changing picocell locations support different client locations. So doing this sort of brute force search for optimal picocell locations is impossible. Hence, finding best picocell locations is non-trivial problem. Since deploying picocells effectively requires the knowledge of environment, we must find a way to understand the environment accurately with limited number of observations. So how can we understand the environment effectively? Let's look at the fundamental difference between the camera image and the reflected signal profile. In the camera image, we can see that it covers almost all the visual points in the environment. However, millimeter wave device only shows signal peaks at 2.35 and 7.5 meter, indicating that there are only two strong reflectors that are contributing towards the reflected signal profile. Thus, in order to understand the environment, we need to find all strong reflectors and their properties in the environment. But is it necessary to explicitly determine all strong reflectors in the environment? Can we use the visual camera image and use some learning-based approach to understand the environment from millimeter wave device perspective? Here is our proposal, which will not require the measurement from every corner of the environment. We collect signal reflection profile from n random locations. After measuring few signal reflection profiles, now we can predict the signal reflection profiles at the remaining locations using learning-based model. This is possible because visually similar objects reflect similarly, and these predicted signal reflections will also allow us to deploy picocells more effectively. However, we face multiple challenges to predict the signal reflection profiles accurately and deploy picocells effectively. The first challenge in SRP prediction is different field of view of visual data and millimeter wave device. Due to different field of view, we needed to remove unwanted points from the visual data. Second challenge is nonlinear relationship between the visual data and SRP, where we observe that we cannot use a simple mathematical model to predict the SRP from the visual input. The third challenge is inaccuracy in transport learning, where we can clearly see that the model trained and tested in the same environment has 1.5 dB median error, while the error reaches more than 10 dB if we test with a different environment samples, even if they have the similar surrounding objects. After we predict signal reflection profiles on all unmeasured locations, we still need to follow the proper deployment algorithm to cover the maximum number of possible client locations. As we see that random and common sense deployment provides low signal strength on majority of locations. So with all the challenges in mind, let's discuss our system overview to solve them. We broadly divide our system into two categories. First, we predict the signal reflection profile by collecting signal reflection profiles and point cloud data together at random locations. We now sanitize and pre-process our data samples to remove irrelevant and unnecessary information. Then we use deep convolutional neural network to predict the signal reflection profiles on remaining locations. After accurate prediction, we use that prediction to deploy picocell effectively using deployment algorithm. We also use the signal reflection profiles for indoor localization and object tagging. To implement our system, we collect samples through our custom-made setup, as shown in the figure. We use the co-located AirTango and millimeter wave device for data collection. Millimeter wave device is operating at 24 GHz and has a bandwidth of 1 GHz, while AirTango uses the RTAM map to collect the visual point cloud data. By doing this process, we have collected over 1.1 million data samples from 16 diverse environments for training and testing. We have implemented our deep neural networks and simulations on MATLAB and Python. Please read our paper for detail on machine learning, implementation, and hyperparameters. One of the first challenges we face is to synchronize the signal reflection profile and the visual data. Additionally, millimeter wave device has a limited field of view, so the reflectors that are outside field of view does not contribute for the signal reflection profile. As shown in the left side, we only use the points covered in the pink area for our analysis, because the main lobe of the beam pattern of millimeter wave device is around 60 degrees. This shows our complete data pre-processing steps. We first extract the points from the visual data using field of view limited by millimeter wave device. We then compute the inverse distance of each points from the transceiver pose and project them to get the 2D image. We use the inverse of depth image rather than the depth image itself because depth is inversely related to the signal strength. We then mask the inverse depth image with the beam pattern from a millimeter wave device to form the mask inverse depth image. We also include the transceiver pose as an input along with the mask inverse depth image because it also affects the signal reflection profile. So now we have processed the input and output that we want to predict the signal reflection profile. But the empirical analysis shows that the similarity between SRP and the similarity between the depth images have a non-linear relationship. Thus, a simple model is not enough to predict SRP from the visual data. Luckily, we have deep neural networks that are very efficient to find the mapping between the nonlinear data. But we want to have a model that have less parameters and memory and are computationally efficient. So we use a mobile net V2 network to extract the features from the mask inverse depth image and finally use some fully connected layer along with pose to predict the SRP at a given location. Please check out our paper for more design details and hyperparameters. In order to test our network, we trained and tested on 4 different environments. Environment A.1 to A.4, composed of different surrounding objects. The figure shows the cumulative distribution function of SRP prediction error for 4 different environments. We are able to achieve around 1.5 dB median error across all environments. But what about if we train in one environment and try to test on other environment that has similar surrounding objects? The median error itself increases by 10 dB, which indicates that the model didn't learn about types of objects in the environment. So our challenge is to make the model robust and environment agnostic, because our idea is to use the trained model on different floors with similar characteristics. This error is expected in the base model because our base model does not account about semantic relationship between the different buildings and only consider the depth of the reflecting points from the environment. To solve this challenge, we propose 2 streamlined processes to extract the features. We first apply semantic segmentation using PointNet for indoor components and extract the global features that carries the information about surrounding objects such as wall, door, etc. Another pipeline is the base model to extract the local features that are obtained through the inverse depth image. We give the 33% weightage to the global features and 63% weightage to the local features to make sure it learns from the both features. The inclusion of global feature in our neural network model forces it to learn not only the mask inverse depth image and SRP, but also the relationship between the semantic label and surrounding objects and SRP. Finally, we also ignore lower signal strength from the SRP so that the network does not have to predict the noise floor. So semantic aware design helps reduce the SRP significantly. Let's look at our results where y-axis is the CDF and x-axis is the SRP prediction error measured in a dB. As we have seen in the base model, the median error itself reaches more than 10 dB. However, the median error drops significantly when we consider the semantic relationship between the different buildings and include the global feature. The median error reaches 1.5 dB when we fine-tune the previously trained model with a few samples from the new environment. The range of the error is tolerable in SRP prediction. We also have SRP prediction over time at different buildings. Please check out our paper for those results. Next challenge we have is in the Picocell deployment, where if we follow the random and common sense deployment strategy, then only few client locations will have higher signal strength, as you can see in the both figure. To find the best Picocell locations for the given environment, we first use the ray tracing simulation to find the SRP at all possible client locations. We then use our prediction model to estimate the error in the signal prediction at that location. After that, we update the SRP from the ray tracing models based on our predicted error at that location. Now, we rank picocells based on how many clients they can serve with the updated SRP. After that, we select Q available picocells and their corresponding location for the deployment. Now let's see how our deployment algorithm helps to find the best picocell locations. We have used the environment A.4 which has a wooden door and glasses and mostly used for offices. We present here X and Y location of the client in the environment, and the color shows what is the signal strength each client receives when standing at the given grid location. Now if we look at the Argus, which is our system, we can see that most of the regions have a signal strength close to 30 dB, which is a significant improvement against the common sense deployment method and the random method. We have more results on Picocell location with coverage area in our paper. Please check out our paper for more results. We can also use the predicted SRPs for localization and object tagging at low light conditions. In both of these applications, we reuse the base model architecture to extract the features and modify final few fully connected layers to steer it for either localization or object tagging applications. For indoor localizations, we predict the object pose, which gives the location and orientation in the test data from predicted SRPs. However, for object tagging, we first place 6 different objects at various locations in the environment. We then measure SRPs at random locations and train the classifier model on that area. Now we predict the SRPs on the remaining locations and use that predicted SRPs to classify different objects. Please check our paper for localization and object tagging results. Finally, let's quickly summarize what we have covered in this presentation so far. We saw how Argus can accurately predict millimeter wave signal reflection profile in the given environment and can generalize across other environments. We also observed how predicted signal reflection profiles can enable indoor localization and object tagging applications. We finally saw how we can use the predicted SRP to deploy Picocells accurately, which is the core challenge in next-G networking. Thank you everybody for listening. Please check our paper for other exciting results, and if you have any questions, please don't hesitate to contact in the given email address. Thank you.